we're going to talk about chapter 19. We're going to make this as short as possible. This is a fairly involved topic. This is the beginning of inference for statistics, a bit of an introduction. We're going to talk about confidence intervals today. Essentially, a confidence interval is a way of predicting an unknown parameter. Let me say that one more time. The purpose of a confidence interval is to estimate the value of an unknown parameter. In this example, we're using GPA. It's a quantitative example. Just FYI, the rest of this unit, the rest of this chapter is going to be entirely categorical, so be careful. It doesn't matter. We're going to talk about these as confidence intervals in a quantitative text eventually, but the idea is the same. If I wanted to estimate the GPA on campus, I could go out and take a load of samples from my population, from my students, and ask them and average all their GPAs. Now, I'm going to be taking a sample, so getting averages like these somewhere in the middle is probably going to happen, right? But it won't be the actual parameter. It won't be the actual GPA because I wanted to ask everyone. I could, if I had enough time and resources, go to the entire campus and talk about what the GPA is. I could get every student's number, average it all together, and I would have the truth. And it would be the point in doing a confidence interval because I'd know the facts. I would know the actual parameter. No reason to estimate it. But usually it's not possible, or it's just not feasible to do it with the resources or the time constraints in real life. And so a lot of the times what we do is we create an interval, a range of numbers using samples. And that's usually good enough to do. For example, here we can see several different examples of confidence intervals or GPAs. Notice they're all centered on 3, but they have different widths. These widths, the interval widths, change something about the interval, right? The widest interval is this one, 2.0 to 4.0, and the most narrow interval is 2.9999 to 3.0001. This is what we're doing is we're adjusting the precision of this interval. Okay, not accuracy, because I don't know the actual value, so I can't even begin to discuss accuracy, but I can discuss the precision of it, right? The bottom one is so precise that it almost isn't very useful to me. I don't feel very confident that the actual parameter falls in there. Now, I'm pretty confident about number 3. From 2.0 to 4.0, that's a really strong likelihood that it's going to fall in there. I mean, I could have probably told you that without even taking a sample, right? It's so wide at this point, it's a little bit useless to us. In that case, sometimes we have to decide, do we want to be confident in our answer, like part 3, the third one here, or do I want to have a lot of precision and nail it down to a specific value, right? And what we find out is that we have to balance these two things out. Do I want precision? Do I want to be confident, right? Sometimes we have an interval that is so wide that it is totally useless, like this one. The high temperature tomorrow will be between 40 below zero and 200 above zero, right? There's no point. Like, that is absolutely worthless because it's so, the width is so wide, it covers every possible combination, okay? A confidence interval tries to balance certainty versus precision, okay? The point is that you don't really need to do that. Now, I'm going to go through these slides. I'll post this up a little bit later if you want to take a little bit more time and kind of go through this. I'm going to hit the high points. We know confidence intervals according to the 68, 95, 99.7 rule. Now, what we've talked about in the past is that we said 68% of all, in this case, it'll be samples, of my p-hats, my estimations of my numbers, right, falls within 1 standard deviation of the center. Notice I said standard deviation, not standard error. This is standard error here. I'll talk about that in a minute. 95% fall within 2, and 99.7 fall within 3. Okay? That means that you have been exposed to this to a certain extent. Now, let's be honest. My 1, 2, and 3 standard deviations that we've originally talked about are a little misleading because they're not exactly 1, 2, and 3. They're a little off, and we'll talk about how much that is in a minute. The margin of error is essentially the part that we're adding to our our p hat. And the p hat is the estimate, right? It's our opening up a bag of M&Ms and I wanted to count out the percentage of green M&Ms. Let's say I had 20 out of 50 M&Ms that were green, right? We would say my p hat in that case would be 20 divided by 50 or 40% or zero point 0.4. Usually we always stick with the proportion in this situation. We want to do p as a decimal value because we're going to be combining it with other things. And so here we would say that 95% confidence because it has two standard deviations. If it were three standard deviations or three standard errors, we would talk about being 99.7% confident, right? In general, the confidence interval formula takes the basic form of estimates here, plus or minus, it's plus and minus actually, the margin of error. Margin of error is related to your standard error, and I'll talk about the differences here in just a minute. What we want to know is that the larger my margin of error is, the wider my interval gets, right? You've seen this on television all the time. If you watch the news for any length of time, a poll will come out, and they're going to say the percentage of people that agreed with this statement was a certain value, right? And you can put it back and forth. The plus or minus, the 3% at the bottom, that is what we call the margin of error. If I had a margin of error, you can see these two here. This is a 95% confidence interval. It goes 2 standard errors below and 2 standard errors above. Here, if we're at 99.7% confident, it's going to go 3 up and 3 down. So this one is wider because you are more confident. You have more values inside your interval. The critical value that we're going to work with, we call it Z star. You see it right here. Okay, this is a special Z-score that will correspond to a confidence level. When you get a moment, grab your formula sheets and you want to go back to the section where it says the T distribution. I think it's the second group of tables. You're going to look down at the bottom and you're going to pay attention to the very bottom 2 rows. You're going to see percentages and just a number just above it. If you look at that, well, you can kind of know you're in the right place, is you're going to see 95% at the bottom, and just above it, you're going to see the number 1.96, right? That's how many standard deviations it really is, not just 2. Okay, we're kind of graduated from the elementary part of this. We're kind of moving into the upper level, and so we need to really be specific. We're not going to be generalizing or estimating anymore. We're going to get the right values this time. The Z-star is important because it plays a part in my margin of error, right? So if we had a specific confidence interval, we drew it out on a curve, it'd look something like this. We have a center at 0 standard deviations, or this would be your p hat, whatever the proportion was. For my green M&Ms, it would be 0.4. I'm going to add 1.645 times the standard deviations, right? That would get me up here, whatever that number is, and down below. If you look up 90% in the table, look above 90%, you're going to see the critical value, or the Z-star, 1.645. Confidence intervals are always centered over their mean or their proportion. In this case, they've drawn this confidence interval as a Z-score. We don't typically do that, but just to kind of show you the Z-star, how many standard deviations out it goes. Notice this, it's always symmetric. So that means that with the area left over, it's going to be half on this side and half on this side. That means you've got 5% over here and 5% over here to accommodate that 10% remaining. The formula for your confidence interval really does come down to this. Now, really quickly, instead of writing it the way you see here on the screen, what I'd like for you to do is write it like this. P hat plus or minus the Z star times. Instead of writing the SE of P hat here, I want you to put this formula in. This is really familiar. This is what we used as standard deviation last chapter. I've been talking about standard error and margin of error, and here's what the difference is. Standard deviation is a description we've used for spread. We can't call this standard deviation any longer because we actually don't know P. The last chapter we did. We used P times Q over N and called it standard deviation. That is exactly what that is. But now we're going to be going into a more realistic approach because we don't really know standard deviation. That's a quantity that is difficult to actually calculate, much less do it in real life in terms of large sample sizes or even populations. So rather than doing that, we're going to estimate standard deviation by using our standard error. The way that is instead of using p, we're going to use p hat. I know that my estimate, as long as I do a good job of my sample, taking a sample, trying to make sure it's not biased, make sure it's independent, all of those assumptions that we check, then I'm going to be doing this in pretty good estimation. I'm going to get a good estimation for p. So by using p hat and q hat in this formula, the name changes from standard deviation to standard error. So I'd like for you to replace this equation up here. So it's going to be p hat plus or minus z star times the square root of p hat q hat over n, all under the square root there. That is your official confidence interval formula for chapter 19. Well, for chapter 19 and beyond. Officially, the name of this one is called the one proportion z interval. And we'll get a lot more into that later. And essentially, this is your notes for chapter 19. We're going to do a lot more when we get into some examples. I highly recommend you take some time and read through the notes, look over them, take a good bit of notes, look at their examples, how they work through them, pay attention to the steps they take and when they use their assumptions and their conditions. Then they work out the mechanics of the problem, the math, actually calculating the interval. And at the very end, they find out the interval and they write a conclusion in context of the problem. Pay attention very carefully. Okay, we'll publish some examples going through those tomorrow, and we're going to talk about panic. How do I actually go from start to finish when I have to do a confidence interval?